Okay, so let's take another look at another data set. I'm going to take a look at one called test scores. Okay, and in this one, we took they did some they were experimenting with different training methods, a standard method and an experimental method, and they wanted to see whether one method of teaching improved a test score greater than another method of teaching. So, in other words, we have a pre-test and a post-test that was taken by each student. Some of the students took the, excuse me, some of the students took the standard method of teaching, and some of the students took the experimental method of teaching. So let's take a look at how we might want to interpret this. Okay, so so this student number one, see if I can't get it highlighted. Student number one took the standard method of teaching. Before she took the course, she got a score of 62. After she took the course, she got a post score test of 74. Okay, it sounds pretty interesting, right? Okay, so now let's see what else we got here. Okay, standard method of teaching. Okay, so now let's say we want to compare whether the standard method of teaching was more effective than the experimental method of teaching. Well, one of the things we might be interested in looking at is how much each person improved depending on which group that they were in. Yes. Well, it's kind of we're gonna do something interesting. You were asking about, oh, what about this transform and so on and so forth. We're going to use that right now. But let's take a look at how we're going to handle it, and we'll decide. Well, it's paired it's paired in the sense that before and before and after, right? That same person took the test before and after, and just like we had the serial, before and after, and so on and so forth. Okay. The only problem is that well, let me see here, pre-test and post-test. Serial. Okay. Let me see. Let me see how I want to interpret this. Standard. Experimental. Pre-test, post-test. Okay. Before I do anything else, I am going to take a look at what's the difference in each person's score. Okay. So I'm going to say, it's the same person. So in the sense that the data is paired in a sense, but I'm really looking at two different. The part that is really different, the part I'm comparing, is whether the person that took the standard training, whether their score went down or up as much as the person that took the experimental training. And they're not the same person. So when I look at the differences are not paired. So what I'm going to do now is I'm going to do something interesting. I'm going to create a new field. Okay. I'm going to go up here. The way I do that in SPSS, okay, this is a little bit of an advanced technique, right? It's not just analyze. I'm going to click on a transform. And I'm going to say, I want to compute a new variable. I want to calculate a new variable. Okay, so now it comes up with a little calculator that I can work with the variables and so on and so forth. Okay, so I'm going to say that this target variable is going to be called the difference. Difference. Okay, difference between each one, the pre-test and the post-test. I'm gonna say, okay, here's the post-test. I'm gonna move it into numeric expression, and I'm gonna say it's the post-test minus the pretest is going to be calculated in this new variable for every one of these subjects. Okay, bingo. I could just double click it, or I could drag it up there. Either way. Okay, so this new variable, this target variable, the new variable I'm making called the difference, is equal to the post-test minus the pre-test. And I'm going to say I'm not going to change any conditions for if and so on and so forth. And I'm going to say okay. Okay, let's go take a look at what happened. Okay, and if I go over here, okay, post-test was 72, pre-test was 72, 10. 79, 69, 13, 12. Isn't that like kind of convenient that like it lets you do stuff like that? And remember what that looked like. I'm going to go in there again, transfer compute variable. You could do a lot. There's a lot of functionality. You look at all the functions you have there, statistical function, arithmetic functions. You could choose different variables. You could greater than, less than, and so on and so forth. You can have logical functions. You can do a lot with this. Okay, not only that, but there's other things there. Transform. You can say recode into different variables. For instance, I could tell it that take everybody that's on the pretest that scored less than 50 and put the number 1. Everybody that scored more than 50 put the number 2. So I can turn this into a nominal variable from a categorical variable, right? Or I can turn it into categories, right? Or ranges and so on and so forth. So I can do a lot of stuff with this transform function. Right now, we're doing the simplest thing of all, which is going to take the pretest minus the post-test. So person number 1, right? The difference between their pre-test score and their post-test score is 10 points. Student number 11, the difference is 12, right? So now I want to see if the students that took the standard education did better than the students that took the experimental or the other way around, right? So what am I looking at? I'm looking at whether the difference is the average difference for the standard group is equal to the average differences for the experimental group. Those are independent samples. They're not paired samples now, right? Two different groups of people. Okay, so let's go ahead and do that. So first of all, before I do that, I know that SPSS is going to ask me to because remember this teaching method, standard experimental, it's going to be my grouping variable, right? So it's going to ask me what's the grouping variable, what numbers are you using? So I'm going to go in here to my variable view, look at where is it? Where is it? Teacher, you see it there? Oh, there it is. Okay. I'm going to click in there. It's 0 and 1. Okay. Good. Just so I know it's not 1 and 2. Good. So I'm going to go back to data view. Actually, the other way I could have done that was just to say, turn off the variable and see. I could see that there's 1s and 2s in there. The value labels, right? Okay. So I'm going to go to analyze, compare means, independent samples. Okay. And I'm going to move in my difference is going to be my test variable. My grouping variable is going to be the teaching method. Okay, and I'm going to define the groups as 0 and 1. I'm going to continue. I'm going to say okay. Okay, and SPSS already did the analysis for us. And there's 1,300 students that took standard method, 760 that took the experimental route. The difference for the experimental was 15, and for the standard was 10. Standard deviation looks pretty similar for both groups, standard error and so on and so forth. And look at this. Again, the significance for equal variances is bigger than 0.05, so I'm going to stick with the top row, right? Okay, and then I look at my t-score. Oh, wow, my t-score is minus 39, right? I think we're going to reject the null hypothesis. What do you think, right? Degrees of freedom, so my significance is less than 0.000. So I reject the null hypothesis because that's less than 0.05. It's super less than 0.05, right? And I accept the alternative hypothesis. Okay, usually it's phrased, if you reject, it's usually I reject the null hypothesis and accept the alternative hypothesis. And if you don't reject, you say I fail to reject the null hypothesis. you don't accept the null hypothesis because you could be 96%, 94% certain that you could reject it because you got a significance of 0.06, but you don't, right? So it's not like you think the null hypothesis is true or that you've proved that it's true. It's that you didn't get it, the data did not warrant rejecting it. So don't say you accept the null hypothesis. Say instead we failed to reject it. Okay, so that's the outcome we got here. Okay, let's see if we let's try another example. You guys at home doing okay on that? Did you catch that? Were you able to keep up with the transform and the and so on? I think they're watching the basketball game. Basketball game doesn't start until 9, so don't go to the TV yet. I just was offering that for the guys here because they got a long ride home. You guys online? Are you okay with that? Still there? Okay, good. All right, you're there. Yes. By doing the paired samples? Well, I can't do the paired samples because remember the paired samples, it's got to be lined up to get, like it's got to be in 2 columns. Or actually, no, wait a second. Wait a second. Maybe I can. Let's see. Let's see see what happens if I try and do that. Well, what am I going to put in the pre-test, right, and the post-test? Okay. It's really finding whether there's a difference between the pre-test and the post-test, which there is a difference between the pre-test and the post-test. Right? The difference for the mean of the pre-test and the mean of the post-test. Actually, we didn't really find a significant difference for that. Remember that mixed up a lot. When you do that, you mixed up a lot of stuff there. You mixed up the experimental group and the standard group and so on and so forth. So I'm not that surprised that we didn't get in it, that we didn't really see. Oh no, look at the t-score. It's minus 129. Yeah, it certainly found a difference between before and after test. Okay, so let's try another day. Let's try another data set. Okay, let me try open database. Open data. Let's go to a more familiar one that we've seen in the past. Let's go to the North Carolina birth group. Okay, in this case, let's take a look at married and unmarried mothers. And let's compare the birth weight for the babies of married and unmarried mothers. This is both samples, right? You got married mothers, unmarried mothers. Let me just see what the values are there. It's 1 and 2, right? Okay, 1 and 2 for married versus unmarried. And the weights, I'm going to do it in ounces, T ounces. Okay, the birth weight. Let's see if there's a difference in birth weight for married and unmarried mothers. So I'm going to go to analyze, compare means. They're independent samples, so 2 different groups. Okay, the test variable is going to be the weight of the weight of the child in ounces. There it is. That's that one. And the grouping variable is going to be the marital status of the mother. Okay, and I'm going to define the groups as, what was it, 0 and 1? Or 1 and 2? It was 1 and 2. Okay, I'm going to click continue. I'm going to say okay. Okay, let's see what I got this time. Well, hang on a second here. Let's see what I didn't mean to do that. Okay, let's see what I got here. I have the standard deviations are a bit different this time. Not terribly different, but a little bit different, right? Okay, if I go look at this area here where it tests for the equality of variances, remember it was 0.66 before, now it's 0.2. It's getting closer to the point where it's going to sneak up on us and tell us they're unequal variances. Not quite yet. We're still bigger than 0.05, so we stick with that line. That you can look at this as being a test that tells you whether you can reject the null hypothesis that the equal variances are assumed that they have equal variances. If it's less than 0.05, you can reject that idea and go to the second line. So our t-score is 5. Our significance is less than 0.001, which means we can reject our null hypothesis. There is a difference in birth weights for married and unmarried mothers. I don't know if this data is real or whatever. I know we pared it down to 800 people from 20,000 or something like that. Because earlier versions, student versions earlier years ago, used to limit the number of cases you could have and variables you could have. I think the limit on the number of cases was 800. That's why we use that here. Okay, see if we can't find another prospect. I'm sorry. Well, the null hypothesis is that the mean weight for there's two ways you could express it. One way, which is kind of familiar to what we did before, was the mean weight of children born to married women is equal to the mean weight of children born to unmarried women. However, the way that Professor Waldron suggested you look at this from now on is that really what you're testing is the mean weight of married women minus the mean rate of unmarried women. The difference is equal to 0. And if you look at SPSS, if you continue over, notice that it gives you a 95% confidence interval for the difference, not for the means, but for the difference. What if there was no difference between married and unmarried women? What would you expect that difference to be? It would be 0, right? Well, the confidence interval, 95% confidence interval for married versus for the married minus unmarried was 6 to 12. What's not within that confidence interval? Our original assumption that the difference was 0. So since 0 is not in a confidence interval, we say that the result is different than 0. We reject the null hypothesis. So really, this is doing a test of the difference, not a test of the actual means themselves. So it's probably better to describe it that way as a test of the differences. Okay, let's try one more and then we'll call it a night. How's that? Okay, let's see. I'm going to minimize this. And let's see if I can't get something still out of this database here. Okay. Let's see if I can find something with a little bit more variability. Yes. Oh, now you're talking about proportions, right? That's very interesting that you should bring that up because up until now, we've been dealing in SPSS strictly with means, not proportions, right? With SPSS, proportions get a little bit more complicated, don't they? Because really a proportion is what percentage of the whole group had a disease or didn't have a disease and so on and so forth. For instance, what proportion of married people, let's see, what proportion of married was a proportion of male babies born to married people different than the proportion of female babies born to married mothers, right? That would be kind of a proportion, right? That 36% versus or 51% versus 49% or something like that. Is there a difference in the proportion? For the moment, let's stick to doing that with Excel. Remember that P minus P. There's actually Levi did an example in the presentation on the board. Not only that, but I put a link onto a video that Ali made, which is an example where he actually does this, calculates a proportion and does a proportion using SPSS. And I put a link into our section. It's in his section already. It's in one of 3 YouTube videos that he put up. If you're interested in getting a jump on it, why don't you run through that video and you'll see him convert from a numerical variable into a categorical or a percentage, right? And for the moment, I want to stick with this and kind of move our way up a little bit. I want to do one more that might be an example of independent variables. And maybe if we get lucky, we might actually find one where the variability is different in the two groups. Let's see. We actually do have a couple of proportions here: low birth weight versus high birth weight, premature infants, and so on and so forth. Let's see. Okay, ounces. Da, da, da. Okay, let's try whether or not the birth weight for premature babies was different from babies that were not premature. I'm pretty sure what result we're going to get. Maybe we'll get an interesting result on the variability. Let me just get the view on this. I know what those are. That's 0 and 1. Okay, I'm going to go turn that back on. I'm going to analyze, compare means, independent samples. I'm going to stick with weight of the child in ounces, except this time the grouping variable is going to be whether or not the infant was premature. And I'm going to define the two groups. It's going to be 0 and 1. I'm going to click continue and say, okay. See if I got, if it works. Oh, bingo. Okay. This, I kind of thought this might happen. Okay. So this time, let's take a look at the result that we got. Okay, the mean weight of premature babies was 87. Mean weight of infants that were not premature was 120, which you would expect that to be true, right? Okay, so it's a big difference. It was easily, the t-score is 14, easily proved. Let's take a look at these two possible lines that we might be using to do this calculation. In this case, when I look at my test, what are the variances? The variance, the standard deviation for infants that were not premature is 17. The standard deviation for infants that were premature is 32. It's almost twice as big, right? Oh, went out again? Yeah, sample sizes are pretty dramatically different too. Okay, so, but you see the difference in the standard deviations there? So you might say to yourself, I don't want to assume equal variances here, right? Sample size included, right? So if I go down to my output from SPSS, when SPSS does this Levene's test for the equality of variances, what does it find for the significance? It finds less than 1/10 of a percent. That's less than 0.05. So we reject the idea that the variances are equal, and we accept the idea that they're not equal. And we use the bottom line instead of the top line. In this case, that makes a drastic difference in the t-score that we get. See it there? Because the standard error calculation is different, right? In one case it's 14, in the other case it's 9. Now, that we still reject the null hypothesis, but we do get a different level of confidence, based on that. So if you look at standard error, and if we assume not unequal variance, it's come out to be 3.4 versus 2.2. So in this case, we had an opportunity to see a situation where the variances were not equal. SPSS detected it, and we used the calculation of standard error that involved unequal variances rather than equal variances. Again, we'll go over like actually how to do that by hand. In fact, Professor Waldron actually went through that to some degree in the lecture. So in this case, we'd stick with the lower line. Same result. We reject the null hypothesis in both cases. But in some cases, you can see it can make a difference in whether or not we have the confidence to reject the null hypothesis or not, depending on whether or not we choose equal or unequal variances. Okay, everybody kind of got a handle on this, so that if I threw one of these files at you, you know where to go on SPSS, and what data to move in where, and so on and so forth, and analysis, right? And you guys online, I think probably pretty much the same thing.